Adventers, hi, welcome back to day 17 of our Advent of Code series, where we dissect a puzzle, go behind the scenes, and understand how to approach problems and then try to solve them without writing a single line of code. And once we have the clarity, then only we go ahead and write any code. And the idea behind this series is to help you understand how to approach a problem first and solve it using nothing more than like a pen and paper, and then try to translate into how we can scale it to solve it using our code or machine. And yesterday was really fun. Yesterday was reindeer maze, where we tried to solve a maze puzzle of a reindeer race in the Olympics, and we were able to secure some really good seats. So check that out if you haven't, and check out my playlist for the all last day 16 discussions if you want to catch up. And with that, today we are at day 17, and hence I have this heptadecagon face cam shape around me. And if you have seen the series in the last few videos, I mentioned that by what day do you think the face cam around me would be indistinguishable from a circle? And I remember guessing that it would be around day 22, given the size, as I am stuck in the right corner of your screen. And it seems like we are getting fairly close to that. But yeah, with that, let's open up our day 17 problem and let's get started. Day 17 is called Chronospatial Computer. Let's read it. The historians push the button on their strange device, but this time you all just feel like you're falling. And this is a reference to 2018 day 6. Situation critical, the device announces in a familiar voice. Bootstrapping process failed, initializing debugger. And the small handheld device suddenly unfolds into an entire computer. Interesting. The historians look around nervously before one of them tosses it to you. This seems to be a 3-bit computer, and its program is a list of 3-bit numbers through 0 to 7, like 0, 1, 2, 3. The computer also has 3 registers named A, B, and C. But these registers are not limited to 3 bits and can instead hold any integer. Interesting. So let's write it down. So it seems like we are given a computer, and it seems like it's a very old computer because it only can interact with 3 bits. And oh, on a side note, by the way, if you don't know what this means, I can give you a quick refresher, but pausing the video here and checking out Google about how like these bits operate would be nice. But essentially what we mean by a bit is that our computers operate on Boolean. So where like your each transistor can store either a value 0 or either a value 1. And each bit determines that how much value it can hold. So let's say if we are given a 3-bit computer, it basically means that at a given time, our computer can interact with 3 bits. And what do we mean by bit here is that each bit can store either one of the values, so 0, 1. And since we can store 2 values and we have 3 spaces, that total gives us around 2 raised to the power 3, 8 different combination of bits. And we can see all of those combinations here. If I can quickly write down 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, and 0, 1, 1, 1, 0, and 1, 1, 1. And if you see, these are again 8 combinations, and what they mean is they just mean their values. So 0, 1, 2, 3, 4, 5, 6, 7. That is what that is given to us here, 0 to 7. So this is a quick refresher. Probably you may not need to know more, but it's a very interesting rabbit hole to go into to understand how very simple and or not XOR, XAND, simple gate calculations have today now added so much complexity that we can use these modern systems without thinking anything about the lowest level of abstraction. But let's read on. And it says that it has a program, which is a list of 3 bits number 0 to 7. So we are also given some kind of a program, just like we are going to write for this. And it is a list of numbers like 0, 1, 2, 3. And since it's a 3-bit number, I'm assuming that this will have values 0 to 7. And it says that computer also has 3 registers named A, B, and C. So if I have to explain to you in a very simple term, so a register, you can think of a register as a very small storage location inside any computer that can hold some value. So in this case, we are given that we have a 3 registers, A, B, and C. And it says that they are not limited to 3 bits, which is 0 to 7, but instead can hold any integer, which means it can hold a positive number or a negative number or a 0. And let's read on. The computer knows 8 instructions, each identified by a 3-bit number called the instruction opcode. Okay. So computer, whenever you are giving it a program is nothing but a set of instructions that your computer understands. And it says that this computer only knows 8 instructions. So they are hard-coded into it. And let's talk about instructions. So 8 instructions, they are hard-coded into it. And yeah, so these instructions are also, let me read, represented by a 3-bit number. And that is its opcode, and here it is how it is structured. So we are given an example here. So the 3-bit instruction is the ID of the instruction that is called an opcode. And each instruction also reads a 3-bit number after that as an input that is called operand. So after the ID, we have something called an operand. Okay. So a number called the instruction pointer identifies the position in the program from which the next opcode will be read. It starts at 0, pointing at the first 3-bit number in the program, and except for jump instructions, the instruction pointer increases by 2 after each instruction is processed to move past the instruction's opcode and its operand. If the computer tries to read an opcode past the end of the program, it instead halts. I see. So in very simple terms, what it is saying is that the program that we are given, let's say it's very simple, 0, 1, 2, 3, 4, 5, we are given a pointer, and a pointer is nothing but a reference to a node that initially starts with the 0th position, so the index of this array or the list, which would be same here because I'm using the same numbers, but it takes that, and the first thing that it reads is the opcode. And the second number after the opcode is its operand. And what I'll do is I'll just represent this with 2 different colors. So opcode is your blue color and your operand is this red pink color. So what it is saying, and this is our program, so that is given to us. So I'll just write it here. So this instruction set that is given to us is our program, just like any code. So when the program starts, it first parses the opcode that is given, and then it parses the operand next to it and passes to it. And then this pointer that is given, it jumps by a pointer plus is equal to 2, which means that after this instruction set is done, it starts pointing here to this 2. And in this 2 also, it follows the same pattern where then it passes that, oh, now I need to run this opcode instruction, which is given here. And it passes the operand, like this is what we want to do with that. So basically, in a very simple word, that this is the operation ID and this is the operand on which the operation needs to be performed. And then similarly, the pointer in the next iteration moves to this 4, and we follow the same thing where this is our opcode and then this becomes our operand. But we just don't understand what this opcode and operand means. So let's read on. But we understand that it will skip the pointer by 2 and it will alternate with that. So now let's talking about operands. It says that there are 2 types of operands. So operands is, remember, the pink color where we are, this one, where we are doing some operation to. So it says like, let me write it down, operand. And operands are of 2 types. Let's see what they are. So there can either be a literal operand, and literal operand is the operand itself. For example, the value of the literal number 7 is the number 7. Oh, I see. So literal number, so like whatever the, let's say this was a list. So whatever is the list comma pointer value given, you will just directly parse that as an int value and you will return that. But then there is the another case where there can be a combo operand. And what does combo operand means is that we are just given a simple map where it says that if the value is between 0 to 3, it will represent the value 0 to 3. If the value is 4, it represents the value stored in register A. Remember, we have 3 registers here which are storing some value. If it is 5, it represents the value B. If it is 6, it represents the value of register C. And 7 is reserved and will not appear in valid programs. So that's fair. So in combo, it's just a simple map where we say like if it is 0 to 3, it will basically behave like a literal operand. And if it is 4, we will get the value from A. If it is 5, we will get the value from B. And if it is 6, we will get value from C. And in case of 7, it's basically like a no op. So we won't do anything there and it will not appear in any valid programs. And now the interesting part is the instructions, the opcode, the blue color that we were using. So we are given a bunch of instructions. So let's take a look at that. This is a very interesting problem. It's basically like going through the basics of writing assembly code, like very, very low level code. And we operate on a very high level languages nowadays, like Python, Java, C++, Ruby, all of them almost represents English now. But let's read that. So let's write instructions. So we are given some instructions, which is nothing but like basically what the opcode represents. It represents something. And we are given a bunch of instructions. So total 8 instructions are given. So let's see. The first one says that the ADV instruction, opcode 0. So 0 points to ADV. Let's see what it means. It performs division. The numerator is the value in the A register. And the denominator is found by raising 2 to the power of the instructions combo operand. So again, remember like when you want to read the operand, there are 2 ways. It's either literal or it's combo. So we will have to take these notes here. Just to make it easy, I will represent this by OL and I will represent this by OC. So it's just simpler for us to understand what it is pointing at. And so yeah, it says it performs division. The numerator is the value in A register. So it is taking the value in A register divided by 2 raised to the power of the instructions combo operand. So it will be 2 raised to the power OC that is given here. And I know this is a little complicated to look at, but once we start writing code, it would be fairly simple. We are just going to write a bunch of functions, identify them and try to call them. And it says that there is given an example. So that operand of 2 would divide A by 2 raised to the power 2. Operand of 5 would divide A by 2 raised to the power B because it's following the combo mechanism where it will point to this. So 5 will not be the literal value of 5, but it will be the value stored in the register P. The result of the division operation is truncated into an integer and then written into the A register. So what we are doing is once we do this, we are casting this to an int because it can be a float. We are doing division and then we are storing the value back into A. So we are overwriting the value back into A. Okay, very interesting. So let's see what's the next instruction. So the next instruction has an opcode of 1. It is called BXL. So BXL says that it calculates the bitwise XOR of register B and the instruction's literal operand and then stores the result in register B. So XOR is our exclusive OR. It is a special type of gate or a logical operation that return true when the inputs are different and false when the inputs are same. So in simple terms, XOR means one or the other, but not the both. And I'm going to link some resources here for you to read a little bit more about it. And yeah, XOR is represented by this caret symbol, like whenever we are doing an XOR operation between 2 values. But let's see. So calculate bitwise XOR of register B. So we will take the register P and the literal operand value given in the instruction. So remember the literal value for that we are using OL. So I will use OL. So we will do an XOR operation with OL and we will store this value in register P. So we will store this value in register P. So with that, let's move on. It seems like we have a lot of instructions. So the next instruction is opcode 2. It's called BST. And let's read that. So it says that the BST calculates the value of its combo operand modulo 8. So modulo is our modulus operator. Yeah, I think I talked about that in a couple of videos back. But basically, whenever you do modulus between x modulus y, it gives you back the remainder of that equation. I am going to give you a couple of resources here again to read if you want to read about modulo operator, but let's read that. So we will do the value of combo operand modulo 8, thereby keeping only its lowest 3 bits, and then writes the value into the B register. So here we are taking the combo operand modulo 8. So our combo operand is OC. We will mod that by 8. We will get back some value and we will only keep its lowest 3 bits. So we will truncate this, keep the 3 bits, the lowest 3 bits that were given, and we will store that into our B register. Fascinating. Let's quickly go through the other ones. It seems like we have a long list. The next one is opcode 3. It's JNZ. And it does nothing if the A register is 0. So there is a if condition, like if the value of A is equal to 0, you basically just return and don't do anything. And however, if the A register is not 0, so basically an else, I'm just writing code, I told you, right? It does seem very complex, but when you just translate into code, there will be just a bunch of functions that you will be calling in like a switch case. Sorry for the hint, but I don't even think that qualifies for a hint. But yeah, if this is not 0, it jumps by setting the instruction pointer to the value of its literal operand. Interesting. So remember we had this pointer going on, which we were calling PTR, which was starting with 0 and then was iterating with 2 steps. What we are saying here is that if our A is not 0, the value of A is not 0, we will jump the pointer. So plus is equal to our literal operand value. So we have literal operand value, which is OL. And if this instruction jumps and instruction pointer is not increased by 2. Okay, I'll read it again. So it jumps by setting the instruction pointer to the value of its this. It jumps by setting. Oh, so it's not doing plus is equal to. It is just setting that equal to the value of our literal operand. So like whatever is the integer value, we are just setting the pointer to that. If this instruction jumps, the instruction pointer is not increased by 2 after this instruction. So there is another condition that if it does that, and once you calculate this, the instruction pointer is not increased by 2 after this instruction. This is not super clear to me, but guess we'll just have to write it down. So in the next step, when you move the pointer, it is saying that it will not be increased by 2 after this instruction. So any in the loop, when the time comes to increment the pointer, where we were doing pointer plus is equal to 2, we will probably skip that and we will not do it. Okay, moving on. Let's see. So we have the opcode 4, which is the instruction BXC. And it says that it calculates the bitwise XOR of register B and register C, and then stores the result in register B. For legacy reasons, this instruction reads an operand but ignores it. Okay, so this is, I explained XOR here. So it is doing the exact same thing. And what we are doing is we are taking the register value of B. We are doing an XOR with register value of C. And we are storing it back into the register value of B. And in this case, you will basically just ignore your operand, whatever is given to you. So we will just ignore it and skip ahead. Moving on to the fifth case, which is called out, O-U-T. In this instruction, it calculates the value of its combo operand modulo 8 and then outputs that value. If a program outputs multiple values, they are separated by commas. So output is a new thing. For now, we were just updating the value of register. So here I will assume that by output, we mean either print or we will store it in like an output list or something. But let's write that. So we will take the operand combo. We will do a mod by 8 and we will then output the value. So I'm going to just put like that, you will output the value. And if the program output multiple values, they are separated by comma. So this would be like a CSV, or like, I think my programmatically speaking, it's going to be like a list. So I'm assuming that this output is going. Everything related to computer science is beneath the surface. Looking at the opcode 6 instruction, it's called BDV. And this says that it works exactly like ADV instruction, except that the result is stored in B register and the numerator is still read from the A register. So I will read the ADV register, the instruction again. So ADV instruction said that we will do a division where numerator is the value of A register and the denominator is found by raising 2 to the power of combo operand. And then we were truncating this and we were storing this value into A. In BDB, it says that everything will happen exactly the same, but we will now store the value in B register. So I will just write the exact same thing again. So we take the value from A register and we divide it with 2 raised to the power combo operand, so OC. And in this case, we will store the value, the integer value, into B register. That's what it says in BDV. Yeah. And then we have our last instruction with opcode 7, which is called CDV. And it says that it works exactly like ADV instruction again, but except that the result is now stored in C register. The numerator is still read from the A register. So that's fairly simple. Once you write it, I think we can reuse that function that is calculating. So we will again do the value in register A divided by 2 raised to the power combo operand value. And we will cast that as int. And we will add that into our C register. So we are given an example here of an instruction operation. So if C register contains 9, the program 2,6 would set register B to 1. And then if register A contains 10, the program, so we are given a bunch of different programs. So let's see a couple of them. I will probably not check all of them, but you are welcome to try because this video will then become really big. But so we are given a program initially called 2,6 and our instruction pointer starts from here. It comes to 2. So remember our 2 is pointing to our opcode. So 2 points to the BST instruction and our 6 is our operand. So in this case, we will take the combo operand. So 6 is our OC value. And once you get the value, you just have to put that into the formula that we wrote above. But we can see it calculates the bitwise XOR of register B and register C. And it is telling us that if register C contains 9, the program would set register B to 1 in this case, BST, because we are doing the combo operand modulo 8. So we did 6 modulus. So if register C contains 9, we are doing it here. So we will do, so we will do a combo operand modulo 8, keeping only its lowest 3 bits and writes that value into B register. And we will do 2,6. So the OC value of 6. So the OC value of 6 is the value stored in C. So in this question, that's why our C value is given to us as 9. And if I now do 9 modulus 8, remember that I told you that whenever you do a modulus of a value, it gives you back the remainder. We get the 1 and then we store that value into B as mentioned here. And similarly, I think we are given another case. So let me draw a line so we don't confuse ourselves. Where we are given a program 5051554. So in this case also our instruction pointer pointing with P will start with this, where the first part is opcode and the second part is our operand. And if we see our opcode is initially given 5, so if we quickly see the 5 points to the out instruction, and we are also given in this example that the value of A is 10, and we are not given other values probably because we don't need it here. But if we read the 5th instruction, the out, it says that calculate the value of its combo operand modulo 8. So we have to do OC mod 8 and then we have to just print / output the value. So first what we will do is we have 5, 0. And if we see, like, I remember that for combo operand 0 to this value represents the value 0, 3. So we will do 0 mod 8, which will give us an output of 0. So whenever we do a mod of 0 with anything, we just get back the answer 0. And yeah, so it will give us that, and then the pointer will skip ahead and move here. So then it will go to 5, 1. So 5 is still the same instruction, out instruction. And now what we will do is we will do 1 mod 8. So 1 mod 8 should give us back 1. And now this is going into the output. So if I write output, we have 0, separatedly 1. And then the instruction is run, we'll move to 5. And now it is 5, 4. So here 5 is again the same instruction, which was out instruction given here. And our operand value, which is the combo operand value, because OC is 4. If we see that 4 points to the value stored in register A, and in this question we are given that register A contains 10. So we will do a 10 mod 8, and that will give us an output of 2. So the output hence comes to 0, 1, 2. And similarly, I would ask you, actually, I would request you to do the same exercise for these 4 examples, just to understand what are some of the edge cases that we may be missing here, and try to understand how this will work. But for the sake of brevity of this video and the questions, I'll just move on. So let's read. So it says that the historian's strange device has finished initializing its debugger and is displaying some information about the program it is trying to run, your puzzle input. And for example, so we are given like an input like this. So if I put that in my whiteboard, it looks something like this. So this is how our puzzle input is given to us, where we can see that what are the current values in register A, B, and C, and then we can see our program instruction set. So looking at this, your first task is to determine what program is trying to output. So we are only interested in output. Remember those comma separated values that we were generating. So A, B, C, like whatever the values that were coming. And to do this, initialize the registers to the given value. So we will start with the given values and initialize our registers, and then run the given program collecting any output produced by out instructions. Always join the values produced by out instructions with comma. After the above program halts, the final output will be, so we are given an output for this one where it says the output will be 4, 6, 3, 5, 6, 3, 5, 2, 1, 0. And now using the information provided by the debugger, initialize the registers to its given value and then run the program. Once it halts, what do you get if you use commas to join the values it outputs into a single string? So this is our answer. We don't have to do any fancy calculations. We just have to run this registers, find this value, and put this into a string value separated by comma, and that should be our answer for our puzzle. And if I look at the puzzle input, we can see that we are given the registers value with A, B, and C, and when we are given a program. Interestingly, the part 1, at least, I may be speaking ahead of my turn and again foreshadowing like I have been doing from last few days, but it is going to be a very simple part 1. Probably part 2 is going to be complicated, but if you see the most complex part of this question is to understand these 8 instructions and the whole part around opcode and operand and the difference between literal operand and combo operand. So it's a fairly straightforward arithmetic type of program, but it has a lot of branching and logic in it. But yeah, with that, I hope I was able to explain the question well. And I think this is your cue to pause the video and think about how you would approach it. And remember, we have discussed some of the approach and how we will do it, where I was talking about the branching of the code. But it would be good to think about the structures and how we will put everything in place to get our puzzle answer. And yeah, with that, once you come back, we will discuss some of the hints around how I'm planning to approach the problem. So see you in a bit. And yeah, if you're still here, let's talk about some of the hints for you to write some code and solve this problem. So we'll grab our old orange marker and let's talk about it. So looking at the question, I think one of the first most interesting question here to think about is the data structures. That how would you store all of these values? Because there is a lot of number manipulation going on where we have a bunch of registers, we have operands, we have operators, opcodes, and in operands also we have two types where there is one literal and then there is one combo. And then you are doing a bunch of divisions, multiplications, raised to the power, and like XOR operations. So you need to think about how you would represent all of these things. And whenever I have questions and problems like this, I personally am very biased towards object-oriented programming, but you don't have to do this. But I just find it that when you encapsulate everything into a nice class and put the values, it just makes for a much more pleasant code writing experience and a debugging one as well. And the second hint, if I can tell you, is the instruction execution, because that is the probably the most complicated part of the question, as I explained. Because if you look at these instructions that are given to us, these are the ones that possibly tries to confuse the puzzle solver, that is us, a lot. But like once you are able to put this, I think depending upon how you encode this, maybe using a switch case if you want to do like a very bare bone implementation, or you can write like a function for each opcode. Probably I'm going to do like that, and then just do like what you want to do and then update the values. It will just make it much more simpler. And I think the operand handling is the third part, which is interesting because you can either have a literal operand or you can have a combo operand. And yeah, I think once you are able to pay close attention to these three things, it should be fairly straightforward for you to write code. And with that, I'm going to leave you and I'm going to go and open my VS Code and just write some Python. And once I'm back, we will do a quick retro to see if I end up doing anything special other than all of this here. I hardly doubt that, but guess there is only one way to find out. So I'll see you in a few minutes. Hello, welcome back. And as you can see, we have received our first gold star for the part 1, and we are getting closer to finding the chief historian. But before we move to part 2, let me explain how I wrote the code. As I said, it was fairly straightforward. I started by initializing our all three registers A, B, and C with the given in the puzzle input. Parsing the input was interesting, and I ended up writing this abomination line to parse the program, but hey, it works. And then, yeah, I used a while loop to iterate through the program that was controlled by our instruction pointer, because there was this specific instruction where I wrote it down here, ZNZ. Yeah, this JNZ was interesting instruction because here we had to take care of updating the pointer location to the literal value and ensure that we are skipping the movement where we are moving ahead. But yeah, after that, inside the loop, I just fetched the opcode and operand from the program one by one. And as per all the instructions, I implemented the logic. And the out instruction was also fairly straightforward. I just took the value after modulo 8 and added it to a list. And once we were out of the program, I just joined that list with commas and outputted a string. And in my part 1 answer, I just put that string and it worked. So yeah, with that, let's move on to part 2 and see what we have it in hold for us. Hey, are you enjoying solving these problems with me? So we have been making videos from 17 days now, and I'm very curious to hear your feedback. And if you're enjoying, I would really appreciate it if you can press the subscribe button below. It will really help the channel. With that, let's go back to the part 2. Part 2. And let's read it. So digging deeper in the device manual, you discover the problem. This program is supposed to output another copy of the program. Getting an output that we were using as like a comma separated string that we were inputting. And what we want to say is that this program that we are executing, the idea is that when you take a program and you process it in the question, your output that comes, it's saying that it should be exactly equal to program. Yeah, the program that was initially input. So basically your input and output should exactly be same. And it seems like the value in register A is corrupted. So in our input, we are given a value of A and it's saying that that value is not correct. It is corrupted, which is why our output is now different than the program. And you will need to find a new value to which you can initialize register A so that the program's output instruction produces an exact copy of the program itself. So the idea is we want to find like a new value of this register A so that when we get an output, it should be directly equal to our program that was given there. And for example, we are given test a program here. So let's see that. So it says that we have register A, B, and C, where B and C have 0 values and register A has 2024. And our program is given to us here called 0, 3, 5, 4, 3, 0. And if we quickly run this, so we can see that initially we are given the instruction 0. So let me open the instruction. Yeah, so these are our 8 instructions. So if we try to see here, it says that if your opcode is 0, it performs division. Numerator of the value is in A. So it takes 2024 divided by the combo operand. So that is 3 here, which is 2 raised to the power 3, which is 8. And if we divide this, this comes to 253 value. And once we get 253 value, we write it back to the A register. So now A register will have 253 value. And moving on, it goes to 5, 4. So the 5th instruction is the out instructions, where it calculates the value of its combo operand modulo 8. So we are given 4, and 4 represents the register A, which is the value 253. So let's keep an output here. So that's it's easy for us. So it takes 253 and we do the modulo 8 as written in the 5th opcode and then output that value. So if we do 253 mod 8, that should give us the answer 5. And reading the last 3 instructions, so it says 3, 0. So if you see the 3 opcode is this instruction. And it does nothing if the A register is 0, but the A register is not 0. And if it is not 0, it jumps by setting the instruction pointer to the value of its first literal operand. If this instruction jumps, the instruction pointer is not increased by 2. So it basically is asking us to go back to the 0th position. And then I think we start again. So I get the point. It is going to loop a bunch of times. And it says that if we see this, it produces a copy of itself if the register A is instead initialized to 1. So it's saying like if we somehow change the value of this A to 117440, when we try to run this program, it is going to give us an output which will be again 0, 3, 5, 4, 3 and 0, which is the same as the input that was given. So now it is asking us to calculate that what would be the lowest positive initial value for register A. So we have to calculate lowest positive value of A so that the puzzle input that is given to us causes the program to output a copy of itself. So this is a very interesting question. I absolutely love it. So I think the question is clear. Like what we have to do is that looking at our puzzle input, which was given here, we have to modify the value of A in such a way that when we run this program, it outputs a copy of itself. So we should get back the same 24117515430355530. And yeah, with that, I think our part 2 that's all there is. So I think now is a good time for you to pause the video here and think about how would you possibly approach a case like this and what are some of the theories that we can apply to make it easier. And of course, there is a brute force solution, but I think it would be good for you to think about what are some of enhancements we can make in our code for part 1 that can help us here. And once you're back, we will discuss some of the hints and some of the approach that I'm thinking of taking before I go ahead and write some code. So I'll see you in a bit. And yeah, if you're still here looking for some hints, let's talk about that for part 2. Oops, wrong color. We'll take the orange color. And if you look at the problem, of course, I'm not going to talk about the brute force approach. You are welcome to try, but I'll explain how that would work. So in the brute force approach, instead of starting with whatever the value is given for the register, what we can do is we can probably just do a loop from 1 to I don't know, infinity, like maybe a while loop. I suspect that it is going to run for a really, really long time though. And then the idea is like whenever you reach to the end of instruction and end of program, you will have to calculate that if your program that was given to you, the string, which is it equal to output or not? You are welcome to write that. Maybe that will help you think. But I think there is a more interesting analytical solution that we can use. And this is an interesting way of looking at the problem. So if you look back at the instructions that were given to us, there is a very interesting thing to note that because we only care about output, there is exactly one instruction that contributes to our output string. And that is our this instruction, which has the opcode 5, right? So whenever in our program input we will have a 5 instruction followed by an operand, that would lead us to get the value that we'll get in the final output string. And if you read that, what it is doing is it is calculating the value of its combo operand modulus 8. So anything that is after the 5th instruction, it is taking the combo operand and it is doing a mod 8, and then whatever the value it gets, it is just pushing it to the output. So now an interesting approach here to think is that can you think of a way where we can do some kind of a reverse engineering to maybe start with the output first and use some heuristics to understand that what should be the value of register A so that we can get the output to be equal to the program. And the idea is to deduce the register values. We have to work out backward from the out instructions and get the values there. So I think this is possibly the approach that I'm going to go ahead with. And I think by working backwards from the instructions, we should be able to very quickly deduce the required register values and get the initial, and even if it doesn't give us the full value, we probably can try in some values and see like what is the trend of the output that it is going to, and maybe we will be able to find out a constraint. So I'm going to try that approach. It sounds fair to me. And I think maybe you should also try one of these approach, probably start with brute force, get disappointed, and then move on to a heuristics and analytical approach. And once I'm back, we will discuss in the retro about what is if I end up doing something different.
The next day.
Hey folks, welcome back. So as you can see, finally I was able to solve the part 2. And it's not even the same day, I'm wearing different clothes. So last night I was up till 1 a.m. banging my head trying to find a solution, and I was probably too tired. So I did follow the best debugging technique, which is called sleep it on. So I slept on it. I had my work day today, and after my work day, I got back to the part 2 of the problem with fresh pair of eyes. And like then I was able to solve it. Like it took me around 1 hour to construct it, and I will talk about how I did it. But before that, the today's problem basically reminded me of last year's day 20 pulse propagation problem. And that was a very similar problem where we were given a bunch of symbols and states. And I remember like to solve it, the best way was for me to design a state machine and then reverse engineer that. And problems like these are called quine in computing programming. So a quine is a computer program that takes no input and produces a copy of its own source code as its only output. And it also reminded me of one of this really cool programs, and it's a very old repository, now has 14,000 stars, and I already had started like few years back, which is called Quine Relay. And what Quine Relay does is it's a Ruby program that generates a Rust program, that generates a Scala program, that generates, and it goes through 128 languages. And then at the end, it generates its original Ruby source code again. And you can see this diagram here. Super fun project for you to try and compile on your machine and check it out. And let's talk about like the approach that I followed. So to solve this, I first started with brute force because I just wanted to see like how bad it is. And yeah, I quickly realized that yeah, it's not going to happen. A lot of head scratching entered. But using trial and error, I was able to find out one thing very early on by looking at the patterns, that if I wanted to get a 16-digit output, because my input data, the program that was given to me was 16-digit, the A must lie between two numbers, which is roughly 8 times larger than the another one. So this should be in between, like some x comma y, and these was the lower bound and this was the upper bound. And I spent a lot of time looking at the code, but I was able to figure out these bounds. So this bound was 8 raised to the power 15 to 8 raised to the power 16 minus 1. And minus 1 because we wanted it to be like a 16-digit output. And the idea here was that if you change the value of a register by 1, it affects the first digit of the output and not the last. So last does not get affected. And if you multiply the register value of a into 8, the value it affects, basically the last digit would always be same if register a is greater than equal to 8. And this is important. I'll explain it why. And then I tried building a solution on this with like a semi-optimized approach late at night at around 1 a.m. and it did not work. Probably I'll go back to see, but I soon hit like a dead end, and I was not feeling to do like a brute force on this. Although given that I have a really powerful PC which is built on like a modern CPU, maybe I could have just let it run overnight in a multi-threaded approach, but that's not my jam. So today when I sat back again with a fresh pair of eyes, I was like, okay, let's do the hard part and reverse engineer the program. And what I noticed is that our program is nothing but it's basically a giant loop. So I think that is true for all the input sets. So if you see the last instruction when you output, it asks you to go back to the start, and then it basically keeps looping into it till a is equal to 0. It will keep looping the program into that. And you should check this for your sample data as well. So like whatever program you are given, it will do a bunch of operations modifying the register's value of A, B, and C. And at the end, it's like a go-to statement where it goes back to this and it will keep looping this till your A becomes 0. So in reading the program from the back, I noticed that there is only one operation that updates the value of A based on the previous value of A. And if I open the question here, the 8 instructions. Yeah, the ADV instruction that is given to us. And for my program, what it was doing is it was setting the register value of A by taking the value of A and dividing it with 2 raised to the power n, which is 2 raised to the power 3. And if we transfer this into a bitwise operator, you can see that it was basically shifting my A bit by 3 and then updating the register. And this was an interesting breakthrough because to reverse engineer, I could see that B and C values both depend only on value of A for each cycle. But when we are starting at the beginning, the values of A and B are irrelevant. And hence in my input also, I could see that they are given 0, 0 because they don't really matter. So it is good because it means that we can always test our program by changing a value of A and then see what output is produced. So what I did is I started the reverse engineering of value of A by setting the value of A as 0. And then we need to determine like which previous value would output to 0. And why 0? Because that is the last output of program. Remember, the program will only finish the last output when the value of A becomes 0. So yeah, so the last instruction in our program is the only instructions that modifies A, and all other instructions that were in my program were just modifying the other registers, but that was not relevant for us. And as I mentioned, the last instruction that modifies A for me was the value of A divided by 8, which we can write as like shifting 3 bits. And you can read more about that. I'll probably link some resource below. But what happens in computer science is like whenever you divide a value by 2, it shifts the bit by 1, the leftmost bit. And if we are doing 2 raised to the power n, it basically shifts by n values here. So in this case, it shifts my value by 3, which means that it strips the last 3 bits of our number. So to reverse it, we basically need to add back those 3 bits of number to our existing number that we are starting with, which is 0. And since 2 raised to the power 3 means 8, it means that there are total 8 combinations of the number that could exist there. And this was an interesting theme. Like once I figured out that the value can always be one of the octave, which means that it can always be between 0 to 7, we can only try to add those value and see what it brings to us. So now for me, the idea was fairly simple, that I would generate the initial base case and then I will try all of these 8 values until it matches my program. So the first digit of output, till the first digit of output is the required digit. So I'll compare my output first digit with my program first digit for all these 8 values. And as soon as I will get the value, because our output will grow by 1, as soon as we get the value, we will take this and we will multiply our A by 8, because remember we are doing a division by 8, so moving the bits by 3, and then again start and iterate with these number of values to find the next digit and then the next digit. And finally, we will keep iterating this program till we were able to find. So we had total 16 number of digits in my input program. So we would run this till we found the last digit in our reversed program, and then we can simply return the minimum value of current values for register A, and that was our answer. And I know it might seem a bit tricky because it is disassembly of a program, but I have pushed my code in the GitHub below that makes it a little easier to understand. But this was one of those days where either you go super deep or you have to apply some trick. And once I solved the problem, I went on to the Reddit subreddit to see like what other people are doing. And I saw some really interesting approach where one person broke down the problem, the program that was given to us. And instead of doing this whole sets of instructions and moving around, they just ended up writing it in their own language where, like, let's say while the value of A, and they wrote the whole program. And what helped them is that it was much easier to pass the values to this program and then try to reverse engineer the value that we need, again, number by number. Because at one given of time, we are always removing 3 bits with that X the value of A shifting by 3 bits. So yeah, I hope that helped. And if it did not, just let me know in the comments below. But yeah, with that, we are at end of our day 17. I'm still running behind, so I will probably get started with day 18 before day 19 comes. And yeah, if you enjoyed solving this problem with me, please like and subscribe the channel and share these videos with your friends who are also interested in solving advent of code, whether they are software engineers or not. But with that, I think I will take your leave and you have a nice day. Bye-bye.